Hi everyone, my name is Roshni,
My name is Miriam.
and today we're talking about understanding engagement with COVID-19 tweets.
So, a little bit of context, our topic was COVID-19 information on social media. We know that the COVID-19 pandemic marked a health crisis, but it also coincided with the rapid spread of information and misinformation across several social media platforms. During this time, Twitter was one of those platforms that served as a tool for updates, public messaging, and just overall conversation revolving around the pandemic. So, for our project, we decided to examine how tweet attributes such as sentiment or user connections relate to engagement, which we defined by the number of favorites a tweet receives. And by understanding engagement with these tweets, we were hoping to identify which features, if any, of online communication influence how information, and specifically COVID-19 information, was spread during the pandemic. So, as mentioned before, Twitter played a major role in shaping public understanding and responses to COVID. This included responses to government policies, vaccinations, masking recommendations, and quarantine protocol. And oftentimes, the discussion around each of these topics included so much misinformation that by 2021, 8 in 10 American adults believed at least one common falsehood about COVID. This included that the government was exaggerating mortality rates or that COVID vaccines were causing infertility, for example. And both of those were proven to be false. So, identifying what drives engagement of these kinds of tweets helps explain how information and misinformation spreads on a platform like this. And it may be of use in the future for preventing the spread of health misinformation that tends to erode the trust of the public in public health institutions. So, the data we use to investigate our topic is called COVID-19 tweets, and we found and accessed this through Kaggle. It has 13 variables, which can be seen on the right, including string, integer, Boolean, and date time data, and there are almost 180,000 observations in the data set. Briefly running through a few of the variables relevant to our analysis, we have the number of followers and friends for users. We have the number of favorites on a tweet, the tweet text, and then whether the user is verified or not. A few of the good things about this data set is that it's reflective of real-world social media data, so we can expect the results to be somewhat generalizable. It also includes metadata for each tweet, such as when a user's account was created or when the tweet was posted. And then it also allows for multiple types of analyses, given that there's a variety of data available for our use. Some of the challenges we anticipated when working with this data set include intensive cleaning. The data set was pretty large, as I mentioned, so we had to specify some criteria for narrowing down our data and analyses. A lot of the data was also missing, so we had to decide what to do with those observations that had incomplete entries. And then lastly, there was a lot of self-reported data, such as user locations, which again, we had to parse through and decide if or how we were going to use the data.
So, as Miriam mentioned, before any analysis, the dataset required systemic cleaning. So we went ahead and defined a clear inclusion strategy to reduce noise and focus on a specific subgroup of tweets. And filtering was done using a mix of both Excel tools and custom Python scripts. So our first inclusion criteria was restricting tweets to a defined time window. And although the raw data kind of ranged from July 1st to August 29th, we limited the sample to August 1st to August 29th to limit our analysis to a month with fewer days. Our second inclusion strategy was keeping only verified users, and we kind of used verification as a proxy for trust and assumed that these accounts would show higher and more stable engagement patterns. Our third inclusion strategy was filtering based on follower count, where we calculated the median amount of followers across the remaining users and selected only the top half to ensure that the dataset reflected accounts with larger audiences who were more likely to generate measurable engagement. Fourth was validating that there was topic relevance within the tweet by keeping tweets only containing a hashtag COVID-19 hashtag. And finally, because we plan to run sentiment analysis, we restricted the data set to English only tweets.
So once we completed the data cleaning with the strategies Roshni outlined, we conducted four main analyses to investigate our topic. First was a couple of simple regression analyses to test for possible correlations between engagement and a few variables that we suspected would have an influence on it. This included the number of followers or friends a user had. It also included how many favorites a tweet received, and then the length of the tweet. We then completed a k-means clustering analysis to group tweets based on length and engagement levels. And that was to see if there were any structural similarities in tweets that were highly engaging. We also did a social network analysis to map mention relationships to visualize how information flows based on user connections. And then lastly, we completed a sentiment analysis using the Athens lexicon to determine whether specific sentiment was associated with higher engagement levels. And based on our guiding research, we suspected that tweets with a more intense sentiment would have higher engagement, given that they tend to elicit stronger reactions or emotions from the audience. So, with these four analyses, we were hoping to test engagement across account metrics, user connections or networks, and then sentiment.
So our first analysis was running a regression model to analyze the relationship between four variables. Our results kind of generated that the friend count showed the strongest association with engagement, with a p-value of less than 0.001 and an r-squared of 0.131. The R squared was considerably small, but it was definitely larger than the other models. The follower count had a statistically significant p-value, but a very small R squared, indicating a weak relationship. Tweet length showed no meaningful or significant effect, and the regressions using favorite as the predictor returned a coefficient of 1 and R squared as 1, which is expected because we use favorites as the engagement metric itself. Our analysis for k-means clustering, um, our methodology for this analysis was basically to generate an unsupervised learning analysis of our data set to understand how data was grouped. And our results demonstrated that engagement stratifies pretty cleanly into three levels that correspond to network size, with larger networks correlating with higher engagement.
So on the right is the resulting network from our social network analysis. Each node represents a Twitter user and each edge represents a user mention. So this is a directional network. In terms of the degree distribution, this is a very sparse network, which is indicated by the low median in degree, out degree, and total degrees, which just represents very low interaction overall. The distribution is also highly skewed, meaning that a small number of accounts are receiving extremely high numbers of mentions, the highest number of mentions being 4,800 mentions. And this indicates that attention is likely concentrated towards a very small set of high profile accounts. Betweenness centrality was also very low, with only a few accounts acting as bridges. Most interactions are direct mentions to central accounts, which kind of reinforces a structure where communication is broadcasted towards the more influential accounts rather than being exchanged through smaller individual accounts across the network. And overall, the network is highly unequal, given that it's dominated by a few powerful hubs or accounts that attract a large number of mentions, while most accounts have minimum connectivity and low centrality.
Our fourth analysis was an affin sentiment analysis, and the methodology for this was first tokenizing our tweets and matching it to an affin sentiment lexicon to generate the sentiment score for each post. And these sentiment scores were then kind of merged back into the data set and examined in relationship to engagement. And the relationship between sentiment and engagement was assessed using correlation analysis, um, as demonstrated in the scatter plot. And our results demonstrated that sentiment versus engagement showed that tweets with the highest engagement clusters were around a composite score of 0 with only a couple of scattered outliers. And based on these findings, we conclude that extreme sentiment does not appear to play a substantial role in determining a tweet's virality. Conclusions. Um, Regression demonstrated that engagement on Twitter appears to be a combination of features, and K-means demonstrated that clusters were primarily separated by engagement and not by friend and follower count, indicating that high engagement tweets do not necessarily come from users with high follower counts. The social network analysis demonstrated that conversations seem to be dominated by a handful of central accounts, with most users contributing minimally to the network connectivity. And sentiment demonstrated that our analysis um, had mostly neutral or mixed tone tweets that were viral in our data set compared to the strongly emotional tweets. In terms of next steps and limitations, we had identified that it appears Affen lexicon analysis has poor performance on domain-specific language because Affen was developed for general English and not public health or crisis communication language. It doesn't really include many COVID-specific terms like lockdown or quarantine or PCR, even though they may kind of carry emotional weight, but are generally scored as neutral. So in the future, we're interested in looking at using a domain adapted sentiment analysis model that better captures emotional tone of pandemic related language. Thank you.